Hey everybody, so these four statements here, conditional statements, are really famous ones, and if you don't know them, I will write what they are. This is kind of just your, standard, we'll just call this like the normal case right here. This is something called the converse. So if you just do Q implies P, it's called, if you reverse it, that's just called the converse. This is called the contrapositive, and this is called the inverse. And these are kind of the classic four if-then statements. And if you do it out, I don't really want to spend the time because I think you guys could figure this out, and you'll also see it in the book. But if you do out a truth table for these two, you would notice that P implies Q has the exact same truth value as not Q implies not P. And also, if you do out a truth table for the converse and the inverse, you would see that those have the exact same truth value. So when we prove things in math, sometimes we might, we're maybe given this as our normal if-then statement, and we want to show if this happens, then this happens. But it might be really, really hard to do it direct, from P to Q. So a common way that we prove things in math is we actually work with what they call the contrapositive. And if you show not Q implies not P, then that will have just as much meaning as proving P implies Q, because they're really equal statements. Same thing here. If you were trying to show that the converse, you can just work with the inverse, because the inverse and the converse say the same thing, or vice versa. So these are things called logical equivalences. And there's two others I just want to kind of show. Hopefully you've heard of these things before. I thought this was funny. I saw this online when I was getting these things. But De Morgan's is just the idea where, and it's almost easiest, I think, with a picture, but if you negate conjunctions or disjunctions, the way in which those work out. So there's sort of a negate and flip is kind of how I see it. So the negation of a conjunction is the negation of each part, but then it flips to a disjunction. And if you negate a disjunction, all of that, you still negate each part, but then you get a flipped symbol and you get a conjunction. You can kind of see it if you look here. So if you take everything right now in teal is in the complement of A and B. And you can see that it's equal if you just kind of go through. So here, I'll do this part first. So A complement would be all of this part. And then B complement, there's a different color here. B complement would be this part. And, nope, I messed up there. Actually, I'm going to undo. B complement would be this part. There we go. But you can see, if you just combine the, purple and green parts, you really would get what's in teal here. So that really is true. This is actually the symbol, you'll notice it looks kind of like these symbols, but when we talk about sets, we, for whatever reason, the conjunction symbol sort of morphs into this N sort of looking thing. They just call it an intersection. And if you have a disjunction symbol in in logic, then it turns into a union symbol. So this is called the union symbol, and this is called the intersection symbol. But they really mean the same thing. Union is read or, intersection is read and. So they're just different symbols for different types of math. I won't go through this one, but you should like test it just to be sure. But if you take the complement of the union, then it's the complements of both and the intersection of the two, and you would get this kind of region here. That's what it would be. So this is just a very famous one. I honestly don't think we're going to use it a ton. I just think it's something that you all should kind of see. I know I teach it in geometry, but you didn't have me for geometry, so I wanted you to just see this one. So this is going to be our first little like proof, just to kind of get an idea of how like contrapositive kind of works here. So I'm going to take an example this is from a field of math called number theory, and there's a formal definition for what it means to divide something. And the symbol looks kind of weird. This is very normal way to write this. So when we say like A divides B, we actually write it this way, where it's like a vertical bar. So that's red, A divides B. And what that means, so A divides B, if you have B equaling A times something, where that something is just an integer. I think it's always good to like think through something. So let's say I'm just trying to 3 divides 12, right? And you could think that 3 divides 12 because 12 equals 3 times 4, and the 4 is like the C in Z, basically. But that's all this means. And I don't know if you've ever seen the definition of even and odd, but that's actually the formal way that we define evens and defines odds. Basically, it's just 2 times something, where that something comes from Z, and 2 times something plus 1 is an odd. Some people don't know, but like 0 is an even number. Some people are like, is 0 even or odd? It is definitively even, because it fits this definition. Also, some people don't realize, but like -3, -5, things like that. Negative numbers are odd numbers, and you can also have negative numbers that are even numbers, like -4. Some people don't realize that even and odd can be negative, but they absolutely can. This A being from Z means that, negatives are even and odd numbers. Some people, for some reason, think that even and odds are just positive numbers, but they're negative, and 0 is also even. So I wanted to kind of show you why contrapositive could be useful here. So if I tried to do this little like proof down here just straight, I have that N is odd, and that's kind of like my P, and then it's going to imply that D is odd. It's like my Q. If I just did it straight that way, okay, I'm going to like assume that N equals like 2, I don't want to use N, I'll use M plus 1, and I will try to show that like D equals like 2 times, alpha plus 1, okay? The only thing I have is that D divides N, so that means that like N equals, something like, I'm trying to think of another letter I haven't used, we'll use beta. Beta times D. So I could say that like beta times D equals 2M plus 1. But what would be tricky is like, how am I going to take this thing and like do some math there and conclude that D equals 2 times something plus 1 for something in Z? And this is an example of something that's like really easy if you just do contrapositive. So you might try things this year where you try to prove it straight. You just start here and you try to show this thing. But if you try something out, you might get to a point like this and you're just like, I have no idea how I'm going to go further. It can be really tough to show that kind of thing. But if I do it contrapositive, so I'm going to basically write up how I would prove this. So we will assume basically that D is even and show N is even. I'm going to even try to write this up kind of nice. So we assume D is even and show N is even. So D equals like 2 times M for some integer M. Okay. And we know that D divides N, so that means that N equals like, I'll stick with this beta, I guess, beta times D for some beta in Z. And so, if I take my D, okay, so I'm going to take this, and I'm basically going to do substitution down here. I would get, let's see, so that means that N would equal beta times 2M, which is the same as 2 times beta times M. And we know that if we multiply two integers, it's still an integer. Therefore, right, we know N is even, right? Because N equals 2 times an integer. And that was exactly what I needed to show. So then we can just like, we could say something like, since P implies Q is logically equivalent to not Q implies not P, we conclude N odd basically implies D is odd. So even though we didn't work with N being odd, we still get the result we wanted because the contrapositive and the original conditional are the same. They have the same truth value. So these are just other ones that I kind of wanted you to see. So this one, very, very famous, very, very useful. There's lots and lots of times where you can't do this as easily, but you can do this one. These two are just super famous. They're really good in computer science. There's like a ton of other places too, but I don't honestly know of a time where we will necessarily need that this year, but they are useful. And I also just wanted to show that, like, the commutative, distributive, and associative properties kind of work. So maybe you want to, like, for some reason, kind of in a sense distribute that P through here. You can do that with these symbols, and it kind of just works the way you would think, like P and Q or R would be P and Q or P and R, and so on and so on. So these are all like logically equivalent. If you do the truth value for like this thing right here, the truth table, the T's and F's in that truth table will be exactly the same as the T's and F's in that. And if you don't believe me, you should try it. And really, like, when I used to like prove a ton of things, sometimes it would be really hard for me to think of like how to do something that I was given like on the left, but for some reason I could do this problem instead. But since I would need to make like a truth table, but I could figure out like, oh, that says the same thing as this. So if I just solve this problem, it's the same as solving this problem. That's like the power of like logical equivalences.